What's up, everybody? Hey, so this is just a way to kind of recap some of the stuff we've talked about in class, and for folks that aren't here or haven't been here, get a little bit into what we did with the significant figures. So first of all, first page right here, definition, all the known digits in a measurement plus that one last estimated digit. Now, what makes it known? A known digit is one that we have lines for on the device that we're using to measure. So for example, with any centimeter meter stick or centimeter ruler that we use, the last line is for a tenth of a centimeter. So that means you would know every number up to a tenth of a centimeter. And that means that you would need to estimate that one last digit to be a hundredth of a centimeter. So anytime we measure with a ruler in this class, and it's a centimeter ruler or a meter stick, you need to be accurate to the hundredths place in terms of your measurement. If you cut it off short from that, then you're not using the device to its full potential. Oh, the potential speech. If I had $1 for every time I heard that one from my mom. If you just tried harder. All right. Now, in class, we did this. We went through, we kind of practiced it a little bit. And so we ended up looking at this idea that we should have been accurate to the hundredths place when we measured the width of the lab bench. So you should have had numbers like 141.57, and then the 7 would be the underlined estimated digit. We didn't really talk about this too much. We kind of skipped it, but some reasons why people would have different answers would be a couple different things, right? There's where you looked at the meter stick when you were making your measurement. That's that whole angle thing. If you were looking at it a little bit to the right, a little bit to the left, or straight over the lab bench, that could mean a difference. But then even if you were looking at it in the same way, you're going to have different answers for the measurement just because your estimation might be different than another person's. Now, all the rest of the digits should be pretty much the same. So for example, when I was walking around class and watching and looking at people's numbers, everybody had something like 141.5 or whatever. And then that last number is going to be different. So if you're using the measuring devices correctly, and if everybody's kind of looking at them the same, you're going to end up with maybe that last digit being the only one that you have that's different from other folks. All right, keeping track of significant figures. I'm going to move this because I think it's blocking a little bit of our view. Hey, look at that. I didn't even know that could happen. That was amazing. I just moved my head. With this, counting rules, right? Here's the rule I get from this first one. Any zero in between two non-zero numbers counts as significant. Zeros at the end of a number only count if there is a decimal place. Zeros at the end of a number only count if there is a decimal place. And those zeros count whether they're before or after the decimal. Any trailing zeros at the end of a number count if there is a decimal place. Otherwise, these two zeros here are simply placeholders. This is telling us that I had a measuring device that, for example, maybe had a 0 at one end and 1,000 at the other. And I estimated that it was about 4/10 of the way. So that is an estimated 400 in that particular measurement. This one tells me I knew the 4, I knew the 0, I estimated that it was right on that line for 0, and so this is my estimated digit. And to show that they count as being significant, I include the decimal place. Zeros at the beginning of a number do not count. These are simply placeholders as well. Even if there were lines for this, the object I'm measuring didn't start to show up until right here. So these can't be counted as significant because they're not even part of the value of the measurement that I'm doing. Again, just simply placeholders, setting the place of my decimal. And then here again, showing these at the beginning are not significant. This one at the end is. So answers for the thing below here, this one would be 3. The 2 ending zeros don't count. This would be 2. The 2 beginning zeros don't count. And then hold off here for just a second. Let that go away. There we go. This is 6, this bottom one. The 7, the 2, and the 9 count. The 0 in between the 7 and the 2 count. The 2 at the end also count because, again, decimal point. All right. Next, adding and subtracting. We talked about the fact that when you're adding and subtracting, you have to line up the decimals. Anytime you add or subtract, you are always going to round your final answer to the fewest number of fewest number of decimal places that you saw in your measurement. So for example, I have the tenths place here, the hundredth place here, and the thousandths place here. My final answer can only be as accurate as my least accurate measurement, which is to the 10th place. So that is why this 17.275 got rounded to 17.3. Again, 3 decimal places here, 1 decimal place here. This is my answer my calculator gives me. I round that to 1 decimal place. No decimal places, 1 here and 1 here. I'm sorry, 1 here. So my final answer has to get rounded to no decimal places, to the units place here. 2 decimal places, 3 decimal places. My final answer has to get rounded to 2 decimal places. So answers for this one that we saw in class yesterday, I believe this one was 10.49, which gets rounded to 10.5 because I can only have 1 decimal place. The one on the bottom was like 23.475, if I remember right. And that has to get rounded to 23.48 because, again, there's only 2 decimal places in the 0.65, so we have to get rid of that. Now, I don't think we got to talk about this with any classes yesterday when we were going through this. So multiplication and division is a different set of rules than addition and subtraction. Multiplication and division, your final answer gets rounded to match the significant figures in your least accurate measurement. So, for example, 2 significant figures in 3.5, 3 significant figures in 10.3. My calculator spits out 36.05. I round that to 2 significant figures, not 2 decimal places, 2 significant figures to match this. Here, again, division. I have 4 significant figures here, 2 significant figures here. Look at this big old long number with all these different things and all this carrying out and carrying on a calculator that you're going to get here. I don't want all of that. I don't need all of that. Not all of that is actually going to pertain to my answer based on these numbers here. I have to round this to 2 significant figures. So I have to round to this 7 right here. The 3 keeps it 2.7. Here again, 3 significant figures, 4 significant figures. This is what my calculator gives me. I have to round it to 3 significant figures. 1, 2, 3. The 8 rounds up, 36.4. So in these, when you're doing these, whatever your calculator gives you, there's 5 significant figures in 100.50, 2 significant figures in 5.5. My final answer can only have 2 significant figures. Same thing here, 3 significant figures in 2.65, 2 significant figures in 9.7. Whatever my answer is should have 2 significant figures. Lots of times if we're doing these types of things and I'm grading them, all I do is check it to make sure you have a correct number of significant figures. I'm assuming you can punch numbers into a calculator correctly. Sometimes we make mistakes, but we're going to go ahead and mostly be looking at, did you carry through the correct number of significant figures? Peace.